In this video, we'll be introducing two special types of sequences. No, not the Fibonacci sequence, arithmetic and geometric sequences. Let's get started. We begin by defining an arithmetic sequence as basically a fancy way of describing a linear equation. Now, if you remember with linear equations, we increased each time by a constant rate of change, basically your slope. That's what's going to happen here. So let me show you what I mean. Suppose we have the sequence whose first four terms are -2, followed by a 1, followed by a 4, or a 7. Okay? Those are your first four terms. Now you can tell, hopefully, what's happening, right? Recursively speaking, you'd start at your first term and you would add 3. That's right. If you add 3 each time, you'll get to your next term by adding 3 to the previous term. So recursively, we could describe this pretty easily. But once again, as we mentioned in our previous video, we would prefer for us to be able to do a little bit higher level thinking and write it explicitly for our reader and for our technology. So what we'd like to be able to do is to write this general term, and this will be our first of 5 formulas that we'll be doing in this video series. Okay, so our first formula will be for the general term of an arithmetic or a linear sequence. And so what we're going to do is we're going to build it together. I've already shown you in the notes kind of the template for what's happening, but let's take a look at where it came from. If I wanted to figure out, for example, the first term, it was -2. Okay, fine. The second term, I'm going to write them out with you, was 1. The third term was 4. And the fourth term was 7. But let's see if we can find the pattern, just depending on the first term and adding a common number each time, which we'll call the common difference, d. Now, we mentioned already that the common difference, d, was like your slope, right? It was the number that you're adding each time to get from the previous term to the next term. And you could find that common difference by simply finding the difference, subtracting 2 consecutive terms, and seeing that it's the same each time. In other words, the difference is in common, the same. So 1 minus -2 gives you 3, 4 minus 1 gives you 3, 7 minus 4 gives you 3. Thus, we have a continuous rate of change, a constant rate of change, called the common difference, d. Works just like the slope. So what I like to show you is that to get your first term, you really added no copies of d, where d was 3, right? You added no copies of d. It was just -2, right? But in the situation here, where you got a 1, you started with your first term of -2, but you really added 1 copy of d, where d was your common difference, 3. Because -2 plus 3, well, there's my 1, right? Similarly, to get to the third term, if you started at -2, how many copies of 3 did you really add to it? That's right, you added 2 copies of 3. Because -2 plus 6 is +4. That was our third term. Similarly, to get to the fourth term, starting at your first term of -2, how many copies of 3 did you add? That's right, you added 3 copies of 3. In other words, that got you to 7. You're starting at your first term, and you're adding 1 fewer than your term number, aren't you? 0 is 1 less than 1. Let me grab another color so you can see it better. 0 is 1 less than 1 for that term number. 1 is 1 less than 2. 2 is 1 less than 3. And 3 is 1 less than 4. So it is, in fact, true that you're adding n minus 1 copies of your common difference. So this completes our first of 5 formulas for this video series. Today we'll do 2 of them. Okay, so that will be the general term for any arithmetic sequence. And again, what does it mean to be an arithmetic sequence? A sequence where to get from one term to the next, I'm repeatedly adding or increasing by the same number each time or decreasing by the same number each time. So d can be positive or negative. Now let's write out our general term for this particular problem. So for this problem, we would say that our nth term, a sub n, would equal our first term using our formula here, which was -2, plus n minus 1 copies of d, where d was, in this case, 3. Now, you could stop there, and technically that is an appropriate formula that gets you to any term using the term number n. However, there could be an easier way of writing that, isn't there? If we just distribute that 3 and combine any like terms. Go ahead and do that, and what do you get? That's right, you would get 3n minus 3 minus 2. Well, that's 3n minus 5. So watch your arithmetic. A lot of students make arithmetic errors when they're going too fast, or they're not thinking, or they're tired. So for example here, if you wanted to check that this formula is truly your general nth term, you could plug in any of these term numbers. Like for example, when n is 4, we're supposed to get the term 7. Check it out. 3 times 4 is 12. And 12 minus 5 is, that's right, 7. So it does in fact appear to be the general term for this arithmetic sequence. Again, the beauty of writing an explicit formula for your general nth term is that now if anyone knows the term number, whether it's the 10th term or the 100th term, they can simply input that number as n, and they'll have the output for that term itself. Okay, so we've discussed one type of sequence. Okay, great. The one that we're going to describe next is going to occur a lot in your future math classes, and that one is the geometric sequence. Now, just like we mentioned that arithmetic sequences were basically linear equations, similarly, geometric equations are basically exponential equations, which we studied in a previous series, right? So just like we had this idea that arithmetic were linear equations, like mx plus b, similarly, our geometric sequences are repeatedly multiplying by the same number each time, which creates an exponential model. So in our equation here, I'm going to claim that we're going to get our nth term by taking our first term and multiplying repeatedly by the same number over and over again. That same number is called your common ratio r. But let's take a look at where this is going, okay? So if we had an example, like negative 16 as your first term, positive 8 as your next term, negative 4 as your third term, and positive 2 as your fourth term, how am I getting from one term to the next? Can you see the pattern? Yeah, each time you are multiplying by something, what is it? Yeah, negative 2, good job. You're multiplying by negative 2 each time. Now you could tell that that's your common ratio by simply taking two consecutive terms and dividing them. 8 divided by negative 16, in this case I should not say negative 2, but negative half, I apologize, I went too fast for my own good. 8 divided by negative 16 is negative half, you're going down, not getting bigger. What about if you take 8 times negative half, what would you get? That's right, negative 4. And what about if you took negative 4 and multiplied it by negative 1/2? That's right, you would get 2. You're cutting in half and you're changing the sign each time, okay? So in this situation, we would say we have a common ratio of negative 1/2. So in our example, r is negative half. Now as we move into our next videos next time, we'll talk about the fact that when you have a geometric sequence where the absolute value of your r is less than 1, meaning that it's an improper fraction, okay? So a proper fraction. Whenever you have a proper fraction like this as your r, what will end up happening as you start adding up the terms of these types of sequences is they will telescope. They will start to approach a single number. They'll converge to a sum when we take an infinite sum. So that will be very important next time. So hold on to that piece of information. But for now, let's see if we can write out this general term together. So in general, we noticed a pattern here. For my first term, I started at negative 16, and I didn't multiply by any copies of negative half, did I? So that's like negative half to the 0 power. But for my second term, I still started at negative 16, but this time I multiplied by 1 copy of r. And to get to my third term, you get the idea hopefully soon, if you haven't already, starting at your first term, you multiplied by, that's right, 2 copies of r, where r was negative half. So what is going on here? Aren't you really saying that you start at your first term and you multiply by how many copies of r? One fewer than your term number. So what would my exponent of r be? Yep, that's it, n minus 1. This is our second of those 5 formulas we'll be learning in this video series about arithmetic and geometric sequences. So this formula here, again, is your general term for any geometric sequence, your general term for geometric sequence. Using that information, could you write out what this particular example's general term would be? Let's take a look. So you would do it and you'd say, well, my general term should be a sub n equals my first term, which was negative 16, times my common ratio, which was negative half, good job, all to the n minus 1 power. This would be my sorry, it's a little ugly to see there, but this would be my general term. Negative 16 in parentheses times negative 1/2 in parentheses, all raised to the n minus 1 power. Again, always check to make sure that your formula works. Does it truly describe these terms? You could plug in any number, for example, the fourth term. That fourth term should produce an output of 2 for my term, right? So when n is 4, what would that mean? Well, I would replace n with 4 in my exponent, and 4 minus 1 is 3. Then I would multiply, because of my order of operations, negative 1/2 to the third power. So if you take negative half times itself 3 times, what would you end up with? That's right, a negative 1/8. That would mean you'd be multiplying negative 16 by negative 1/8. Well, they're both negative, so the answer is positive, and 16 cut by 8 is really 2. So we're going to have the answer that we wanted, which was 2. Okay, so this is in fact one way to describe the general term of this sequence. Now, there are a couple of other ways to do it using the tricks we used in our last video. So if you could do it a different way at this point, feel free. But what we're trying to teach you today is a shortcut to get the explicit general term for any arithmetic or geometric sequence. So make sure you write those formulas down correctly. I would recommend practicing them each time, writing them out each time when you do a problem, so you can recognize what they are very quickly. Again, this will be really important as you move into your higher level math. So let's take a look at our next example to put these into action. Example 1 says, can you determine whether each sequence is arithmetic or geometric, and then find the nth term? So we begin by looking at the sequences. In part A, we have 1 followed by negative 2, then 4, then negative 8. In B, we have 10 followed by 7, then 4, and then 1. Notice the ... in each of those cases means that these sequences go on forever like that. So take a moment and pause the video and see if you can come up with the answers. Are they arithmetic? Are they geometric? Are they neither? All right, there's lots of different sequences out there, but today we're focusing on these two. Okay, let's see how you did. So for the first case, did you add each time by the same number? Did you multiply each time by the same number to get to your next term? Yeah, you multiplied. Good job. So in the first case, we're really multiplying each time by what? Negative 2. How do you know it's negative 2? Well, if you were to divide consecutive terms, negative 2 divided by 1 would be negative 2. 4 divided by negative 2 would be negative 2. Negative 8 divided by 4 would be negative 2. So since we have a common ratio of negative 2, this is in fact a geometric sequence. And again, the shortcut to come up with the nth term for a geometric sequence is to recognize what the pattern was. The pattern was to get to the nth term. You can look at your notes if you need to, but over time, try to memorize it. Yeah, that's right. Start at your first term and multiply the common ratio n minus 1 times. So that's your exponent. So a sub 1 times r to the n minus 1 power was our template, if you will. It's always going to be the pattern for the general term of a geometric sequence. So let's take a look and fill that in, if you haven't done so already. You put your first term in, which was 1. You put your common ratio in, which was negative 2. And you raise it to the power of n minus 1. So in this situation, your general term was 1 times negative 2 to the n minus 1. Now I want to tell you a cautionary tale for this problem and the one we just did a moment ago in the previous slide. Notice that it's very tempting to multiply 1 by negative 2 here, or in our previous slide we had, I believe, negative 16 times negative half. Very tempting to multiply there first. But we've agreed, if you're going to do math, we've agreed to follow a certain order of operations. And that order of operations, if you remember, in America we use PEMDAS, in English system it's BIDMOS, but the basic idea was grouping symbols first, and then any exponents or indexes before we do any multiplication or division. Right here we have an exponent, don't we? So you have to do that operation first before you can multiply by whatever's in front. So be very careful to avoid wanting to multiply before you do that operation. So in other words, leave it alone. Don't try to simplify, because most of the time you'll make a simplifying error. Okay, so we've come up with a general term. Again, you can test that to see if it's working by plugging in any term number and seeing if you get the appropriate output at your term. What about B? Did you pause the video and try it yourself? If not, recommend doing that. So if you try B here, what you would have noticed is that to get from 10 to 7, and to get from 7 to 4, and to get from 4 to 1, each time we were doing what? That's right, we were adding or subtracting by the same number. In other words, we had a common difference, and what was that difference? If it's going down, it'll be negative. That's right, -3. Now here's how you could have seen that. Subtracting consecutive terms, like 7 minus 10 is -3. 4 minus 7 is -3. 1 minus 4 is -3. I'll erase that because that looks pretty nasty. Oops, get my eraser here. Okay. So yes, in fact, that's exactly what we did. We found that the common difference was in fact -3, which means that this is what kind of sequence? Good job, arithmetic. Now it looks like the word arithmetic, so if you say that, that's totally fine. I know what you mean, but typically we pronounce it arithmetic when we're dealing with sequences. Okay, just so you don't sound like you don't know what you're talking about. Okay, so for an arithmetic sequence, what was the general term? It was a sub n. You can look back at your notes again until you memorize it. But instead of multiplying the first term by r, we, that's right, add to the first term how many copies of your common difference d? One fewer than your term number. That's right, n minus 1 copies. So this is what we'll write down as our template, as a shortcut, to come up with the general term for any arithmetic sequence. So let's see what this looks like in our example. We would have then our first term of 10 plus n minus 1 copies of d, where d was -3. And again, that's technically correct. You could stop there, but it just looks a little bit unsimplified. So let's simplify that for our reader and for our technology. We would get a sub n equals -3n. We usually write them in descending order, so your variable before your constant, plus 3 plus 10. So wouldn't you get positive 13? I've had some students get 7 because they get their sign wrong, so be careful there. You have to distribute the -3 to the -1 to get positive 3, and then add it to 10 to get 13. Now we have our general term for our formula, and we could check it with any term number. For example, the fourth term should give me an output of 1. So plugging in n equals 4, we'd have 4 times -3, which is -12, plus 13, which is 1. So this is, in fact, our general term. Okay. This is a very important skill. If you're going to go on to your future homework problems, to future sections, you'll want to make sure you've practiced this skill sufficiently to master it. Okay? Well, let's take a look at our next example where we put that to use. There we go. In this example, instead of me giving you the first 4 terms of the sequence, I give you 2 random terms of the sequence and tell you, please find the general term for this type of sequence. So let's take a look at what I mean. In example 2, we say, find the general term. So we know what we want here. We like the general term. For what kind of sequence? An arithmetic one. So as I do a word problem, this is a very small word problem, I take it in bite-sized chunks. So I write down what it is that I'm given and what it is that I want. So let's write down what they want. They just told us. They want us to find the general term for an arithmetic sequence. But we know what those look like, don't we? That would be the nth term. And if it's arithmetic, what was the formula again? That was formula number 1. It was the first term, that's right, plus n minus 1 copies of d, where d was my common difference. Now, in the previous examples, we gave you the first term, and it was obvious what d was. Okay? This one's not as easy. Let me visualize for you what's been given to us. Here they've given me some information about my sequence. Just so you can visualize it, here's what we'd say. They've told me that the fourth term is 24. So visually speaking, I don't know my first or my second or my third, but I know my fourth, right? A sub 4 is 24. They haven't told me anything else except that my 10th term is 60. So maybe you already know the answer, but don't tell anybody yet. The 5th term, the 6th term, the 7th, 8th, and 9th, we don't know, but we know the 10th term. The 10th term is a 60, and it continues like that. That's the situation here. We've been given 2 specific terms of this arithmetic sequence. Now, if you already can see a pattern, or if you have a different way of doing this problem, there's a few ways to do this problem, excellent. But what I'm about to show you is a technique that will work for any situation like this, not just the obvious ones. So I would recommend investing in this approach, but if you see a shortcut for this particular type, feel free to use it in the future. Okay, so what is the way that would always work? What would always work is to build what we call a system of equations. Now, why in the world would I bring us back to that knowledge from our previous video series? The reason is, in this particular situation, we have 2 knowns given to us. Let me show you what I mean. We know that a sub 4 equals 24. But we also know what type of term this is. This comes from an arithmetic sequence. And we just wrote above that in general, arithmetic terms behave a certain way. You can get to them by looking at the first term and adding one fewer copy than your term number of your common difference, d. So in this case, this would have come from a1 plus how many copies of d? Well, if n is 4, that's your n here. 4 minus 1 is 3, right? So 4 minus 1, if you need to see it. 4 minus 1 is 3. So 3 copies of d. So that looks kind of clunky right now, but I would like to propose to you that what we really have is an equation with two unknowns, a linear equation with two unknowns, kind of like x plus 3y is equal to 24. If we had another equation with the same two unknowns, couldn't we solve by substitution or elimination or any of our matrix methods using technology? Yeah, we definitely could. In fact, they've given you just enough information to do just that. They've told you what the 10th term is. The 10th term here is 60. But since it's coming from an arithmetic sequence, we know what type of term this came from. This came from starting at the first term and adding how many copies of d? Well, if n is 10 in this case, what is 10 minus 1? It's 9. So 9 copies of d. In other words, we just found another equation with two unknowns. 60 equals a1 plus 9d. Now at this point, again, it's just like x plus 3y equals 24 and x plus 9y equals 60. Solve by substitution or elimination. I'll give you a moment to take and pause here. Solve by the method of your choice or matrices. For example, if you wanted to use your technology, you could say my A1 column has coefficients of 1 and 1, my D column has coefficients of 3 and 9, and my constant column has the numbers 24 and 60. And then in your technology, you could ask it to find the reduced row echelon form, and it would get you your answers, right? Along the diagonal, you'd have 1s, 0s elsewhere, and you'd get your two numbers. Or substitution and elimination work just nicely because it's a very easy system. What did you end up getting? That's right, you should have ended up with A1 is something and D is something. What was it? 6 and 6. Well, that's pretty cute. It doesn't usually happen that way. But now we know what the general term is, don't we? Because if it's truly an arithmetic situation, the general term is your first term, which you found to be 6, plus n minus 1 copies of d, which you just found to be 6. But if you simplify that, the 6n minus 6 is added to 6, which is just 6n. So it turned out to be pretty straightforward. You might have seen it to begin with, and that's excellent if you could have spotted that pattern. It was, in fact, 6 times your term number, wasn't it? 6 times 4 was 24, 6 times 10 was 60. That does make sense. But this approach of writing down what you want, what you're given, and creating a system to solve is a very valuable skill as you move into calculus, pre-calculus, calculus, and differential equations and engineering courses. Very, very important skill. Notice it never said anything about a system of equations. You had to recognize that's what you had and then solve it with the appropriate tools from your toolbox, if you will. Okay, we have one more word problem to do, so take a deep breath. Here we go. Oops, there we go. Example 3. Now this example talks about a special phenomenon in life. Whenever you buy something, like a car, a CD, a DVD, over time it loses value, doesn't it? Okay, now the word that describes losing value is depreciation, whereas antiques, they gain in value typically, so they would appreciate. Most of our items that we buy depreciate. Now there's two different types of depreciation out there. There are things that depreciate with by a certain amount each year, okay, or each however many time you're looking at. That's called linear depreciation or straight line depreciation. Then there's things like this example where your car is depreciating by a percentage each year. You're multiplying by a certain number each year. And that's going to be more of an exponential decay. And that's what we see here. So let's take a look. Visually, I like to usually do a depreciation problem by looking at a little x and y axis, where my x-axis is my time. In this case, it looks like it's in years. And my y-axis is my value. So I'll use V for value. Value here is in dollars, right? And it's going down because it's depreciating. Oh goodness. Okay, so let's take a look at where we start. When time equals 0, so at t equals 0, That's the most natural way to do this problem. I'll also show you a formulaic way in a moment, but I want to show you the most natural way to visualize this problem. When time t equals 0, that's when you originally buy your car. So you buy your car, and this is the price tag of that car, $120,000. So you are a big spender. So that is your first initial value. So I'm going to put a point on the y-axis to represent that value. Okay, so what is happening? Let's do a little bit of thinking. It says every year the car loses 20% of its value that it had at the beginning of the prior year. So for example, after 1 year goes by, what is your car worth? Well, wouldn't it be 20% less? So I have to write this down for some of you, no problem. 100% is the initial amount, minus 20%. What percentage is left? That's right, 80%, okay? So in other words, what we're saying is your car is now only worth 80% of what it used to be worth. So for example, after 1 year, what is 80% of 120,000? What do we get there? 0.8 times that number, right? You're going to get your answer there. That answer is going to be like 96,000, right? That answer is going to be this output right here, that y value. That's your new value, okay? So if we made a little table, you can see what's happening. For your time and for your value that depends on time, you get certain inputs. So when time is 0, you're at a value of 120,000. When time is 1, you're at a certain value of 96,000. And you could notice a pattern here. Each time, if you think about what happened, you multiplied your initial amount of 120,000 by 0.8, but this first time you multiplied it to the 0 power because you didn't need to actually depreciate. That's when you first bought it. But a year later, you really took 120,000 and you multiplied it by 1 copy of 0.8, didn't you? And we won't go through all the work here, but you're welcome to check out the Desmos graph link there. But what you notice each time is you're going to be multiplying 120,000 by another copy of 0.8. And we can see the pattern here, I hope. This is depreciating, and the points will end up looking something like this as we go on. They're not linear, but they are exponentially decaying. So feel free to check out the Desmos graph. It does a much better sketch than I'm doing now. But what I'd like for you to see is a formulaic way of describing what the situation is. The value of my car depends on how many years I've had it, right? It started with my initial amount, and this looks very similar to your exponential models you've done in the past, which was 120,000. And it got multiplied repeatedly by our common ratio, if you will, of 0.8 to a certain power. It looks like the way we've set it up because we started when t was 0 as your initial amount instead of t equals 1, so it depends where you start. We ended up getting our power to be the same as our t, right? As your term number in this case. So it turns out you could say this formula could be described as my value is the initial amount times 0.8 to whatever year I'm in. That's definitely a valid way of interpreting this. Now we could answer the question. They wanted us to find the value after 5 years. So we could simply say v of 5 using our model that we've created. 120,000 times 5 copies of 0.8 after 5 years have gone by. That makes sense. And when you do that, you should get approximately $39,321.60. So that's pretty depressing. After just 5 years, your car, which was originally at $120,000 in value, is now just worth $39,321.60. So knowing when to sell your car is always a good thing to check out. Okay, now if you wanted to do this a different way before I finish off this video, I promise it's almost over. But if you wanted to finish this off a different way, what you could have done is just noticed that you're multiplying repeatedly by the same number each time. That should be ringing some bells in your head. This is a geometric situation, which is why it's an exponential curve, okay? With a geometric situation, didn't we say that the nth term is the first term, a sub 1, times n minus 1 copies of r, so r to the n minus 1? Okay, so is that what we did here? Well, to get to any year's value, a sub n, assuming, of course, that n starts at 1, that's how this one works. Assuming that's true, you would have said that a sub n equals the initial value, which in this case, if it's a sub 1 instead of a sub 0, 120,000. And then you would have multiplied it by 0.8 to the n minus 1. I can't really show that to you because it's getting kind of smushed. But the idea here is you would have had 120,000 times your 0.8, in parentheses, to the n minus 1 power. Well, would that have given you the same answer? Not exactly. If you had plugged in n equals 5, you'd get a different answer. But what you would have had to do is plug in n equals 6, because that would be 6 years after a sub 1. If a sub 1 is where you started, 5 years after a sub 1. If a sub 1 is where you started, 5 years go by, you're looking for a sub 6. And when you plug it into that formula, because 6 minus 1 is 5, you'll end up getting the same result as we had below, $39,321.60. So just be cautious. That's a cautionary tale. If you're going to use a geometric or an arithmetic formula, be sure you recognize that they always start with n equals 1. So if you wanted to do n equals 0, it would look a little bit different. Your exponent would be a little bit off. Okay, but either way of those, totally appropriate. Good luck practicing this. Again, memorize those two formulas, practice writing them down each time, and after you do maybe 3 of these in a row correctly, you'll know that you have accomplished this skill. You've mastered that skill. Okay, so I'll see you next time. Remember, practice a lot because math is not a spectator sport. See you then.